So now we can have another and last look maybe on this task 20 and on this circuit. And once again, after solving it with superposition, which looked like this, and after solving it with branch current analysis, which looked like this, try to solve it with a last method. And the last method is nodal voltage analysis. And yeah, for this we need to know how this nodal voltage analysis works and how the steps are. And the first step was fairly simple. Does anyone remember? We need a reference node, and we still have these 1, 2, 3, 4 nodes, and we can select any of them as a reference node. Usually you would go for the one at the bottom of the network, but at the end it does not matter. So we select this one as a reference node, and the other nodes, we just number them. So, okay, let's say this is node 1, this is node 2, this is node 3, or you could also number them with A, B, and C, but usually you take numbers for them. Okay, so we have a reference node, we have numbered the nodes. Next step.
Draw the voltage drop like
exactly. Introduce these nodal voltages that will be the result of our equation system. So and these always point from each node to the reference node. So we have one nodal voltage like this that we call U10 because it points from node 1 to this reference node. Then we have the second nodal voltage, which is this one here, and we have the third nodal voltage, which is this one here. Okay, and so yeah, then I would say we can directly set up some system of equations in matrix form for this problem here. So we have, because we have 3 nodes, we have a 3 by 3 matrix. I need some more space here. And we have the vector of the unknown nodal voltages, so U10, U20, U30. And here we have our sources. Okay, and so then yesterday we discussed rules, and luckily it was just yesterday in the evening, so there was not so much time to forget about this. Yeah, so we had rules for what happens on the main diagonal of this matrix, what happens on the off-diagonal elements, and what happens in the source vector. So maybe we start with the main diagonal. So on the main diagonal, what elements, or what was the value of the elements? You also look like you remember? Or
it was the sum.
Yeah, it was the sum of the, not the resistance values, but of the conductance values, but of the resistors that were connected to each node. So at this first node, there the resistors R1 and R3 are connected. So we write down this is the sum of G1 plus G3. At the second node, we have 1 and 2 connected. So here it's the sum G1 plus G2, 2. And at this last node, we have 3 and 4, so it's the sum G3 plus G4. Okay, so main diagonal, check. Now we have these off-diagonal elements. What was written there?
Minus G1 and minus G3.
Yeah, so it was always, if I number the lines and the columns in my matrix, so at this position that connects 1 and 2 or 1 and 2, which is in the first row, second column, or second row, first column, it's the the connecting component, the connecting element between these two nodes. And they are always minus. So here it's minus G1 and minus G1. So between 1 and 3, we have this element, minus G3 and minus G3. And between 2 and 3, we have nothing. So there's just a 0 there. Okay, so now of diagonal elements, we can also say check. And I think yesterday we did not really talk about the source vector because we had just one source yesterday. Yeah, but do you know this rule? What happens here in the source vector?
We have the known current that getting in the node.
Yeah, so because remember when we set this up yesterday, each of these equations was a Kirchhoff's current law for each of the nodes. And so here we had the branch currents from these resistors, and on the other side we just had the sources that were connected to each node. So at the first source, at the first node we have this source, and this source is flowing onto the node. So we have plus IS6. On the second node, we just have this source, but it's flowing away from the node. So we have minus IS5. And here at the third node, we once again have the second source, and this is flowing onto the node. So we have it plus. So here, in this source vector, you always have the sources, and it only works for current sources. So here we have the current sources flowing onto and away from each node. And if they are flowing onto the node, they are positive. If they are flowing away from the node, they are negative. And if we would have 2 or 3 sources connected to one node, then we would just have the sum of all the sources, or the difference between the sources if one source flows onto the node and some source flows away from the node. Okay, so now we have our system of equations already, and we can directly put it into Octave. So there's my Octave window. I still have all the resistors there, so I can calculate the conductance values from them. So I can do it for G1 and G2, and of course it would be also possible to save all the values into a vector and to do this calculation at once, but I will do it like this. Okay, and so then we can say now our nodal analysis matrix looks like this, that we have G1 plus G3, then we have minus G1 and minus G3. In the second row we have minus G1, G1 plus G2 and 0, and in the last row we have minus G3, 0 and G3 plus G4. And then the matrix looks like this and does not look too bad. And so then we have the nodal analysis source vector, and in this we have IS6 minus IS5 and plus IS5. And then this one looks like this. And so now we can get our nodal voltages, and the nodal voltages we get from the inverse of this matrix, of this nodal analysis matrix, and then multiplied with our nodal analysis source vector. And we get 3 nodal voltages. And do you remember and recall this value here? It was the voltage that we calculated before, somewhere here as a check of our branch current analysis before. So of course this is not a strict formal mathematical proof that everything that we've done is correct, but it's a good sign that we get some meaningful values here. So this is now the solution of this equation system. If mathematicians or computer scientists look this video, they would argue and say, yeah, this is formally correct, but it's not really the efficient way to solve this system of equations. So maybe, as we also still have some time, if we rewrite this equation here a little bit and say this is a G matrix, and for matrices I will just write these square brackets. And so our system of equation looks like that we have this G matrix. This is multiplied with this vector of unknown voltages that we would like to have. And on the other side, we have this vector of the sources. So this would be this matrix equation in a very short way. And so then remember what we did to solve it. We took the inverse of this G matrix and multiplied it, because the matrix multiplication is not commutative. So the order does matter. We take this inverse matrix and multiply it from the left side onto this equation. And so then here we get inverse matrix multiplied with the matrix, multiplied with our vector of unknowns, and on this side, of course, we have the same, this inverse matrix multiplied with our known source vector. And so then we simplified this, because the inverse of a matrix multiplies with the matrix itself gives,
What's called unity? No.
yeah, well, the identity matrix. So this is the identity matrix, and the identity matrix multiplied with some vector gives the vector, it's the vector itself. And so therefore we end up with that this unknown vector that we would like to have, is what is written there, is the inverse of this matrix multiplied with our source vector. And so this is what I've just inserted into Octave here. This is this equation. And so we could also check if we just take the inverse of this nodal analysis matrix and multiply it with the nodal analysis matrix itself. Yeah, then it looks a bit ugly,
It's rounded.
but it's the identity matrix. So on the main diagonal we always have 1, right? This is 1, this is 1, this is 1, and on the off diagonal elements we have 0. Something close to 0. So this is the remaining numerical uncertainty. A nice identity matrix would look like this. This would be a nice real diagonal matrix with ones on the main diagonal and zeros on the off diagonal elements. And here it's not exactly 0, but it's within the EPS, is the precision of MATLAB or Octave. And you can see that all these values on the off diagonal elements, that they are all smaller than this precision. So they are more or less 0. Okay, and so one idea to rewrite this here would be to write that the inverse matrix could also be written as 1 over the matrix. And so using this, I could also write, okay, this is our source vector. Now, let's do some step in between, right? So instead of this, I could also write it like this. So I could write 1 over G multiplied with the source vector. And this would be perfectly fine. I know, okay, this is the inverse of this matrix multiplied with the source vector. And so then people might say, okay, if I can write it like this, why cannot write it like this? I could also write the source vector divided by the matrix. So yeah, we could write it like this. What is the problem now with this way of writing this equation down? There's an idea? Yeah, this at the end could be the same as if we have the source vector multiplied with the inverse of the matrix. If we write it like this, we don't see the order anymore. And so the cheap trick that mathematicians use in this case is they write a slanted fraction bar. Because the slanted fraction bar shows, we have the inverse of this matrix first, and then we somehow multiply with the second vector there on top. And so they call it, I'm not sure, I think, so they call it left and right division. So I would say this is a left division. And if you would have the fraction bar the other way around, then it would be a right division. But I'm not a mathematician. Maybe I'm mistaken with this. But the long story short thing here in this case is, so we solved our system of equations. Let me make this a little smaller. We solved the system of equations by using it was called nodal voltages, I think. So we used this equation before, or this formula before. The inverse of the matrix multiplied with the source vector. And so that's why the slight problem with this, why computer scientists and mathematicians would say, yeah, this is not the perfect way to solve this. The problem with this equation here is that MATLAB Octave would really need to solve and calculate this inverse matrix first, and then multiply this inverse matrix with the source vector. And if you take the very same equation and write it down like this, so this here is the left division slanted fraction bar, and if we calculate, we see we get exactly the same result. But this is from a numerical point of view more efficient. So what Octave does here in the background is, let's say, directly solve this system of equations without the need to really compute this inverse matrix first. And so, for a 3x3 equation system, it does not matter. For a 3000 by 3000 system of equations, it does not matter. But if you would calculate a system with 3 million equations and 3 million unknowns, then it might matter a bit if you calculate it a couple of times, one after the other, or if you have just not a very powerful computer. So if you would do something like this, let's say on some Arduino, then it would be probably more efficient to do it in this way. So just that if you see somewhere something like this, I've forgotten. I will bring it next time for the exercise. I have a t-shirt of MATLAB, of MathWorks, and there's exactly this formula on this t-shirt. And so you need to know this to understand this, the writing on the t-shirt. This brings us to the old joke and to the old meme that you don't study higher mathematics to be good in your studies. You study it to understand all the math memes and all the math jokes that are associated with this. And so here it's a bit of the same thing. Okay, so back to nodal analysis. We have now calculated these nodal voltages. Are we finished yet? Not really, because okay, we have the voltages, but we would like to have is this current. So how can we calculate the current?
You first need a V1.
We would first need to have this first voltage here, and then if we divide the voltage by the resistance, we would get this current, and then how can we get the voltage?
U10 minus U20.
Exactly. So we take V10 or U10. I'm so sorry. So yeah, this voltage plus this voltage must be the same as this voltage. So this voltage is also the difference between the two, and then divided by R1. So yeah, I can go back to my Octave window here, and so if we want to calculate this, we take from these nodal voltages the first one minus the second one, and divide by R1, and then we nicely end up with the 7.2 ampere that we had before. And yeah, this would be a nice solution using nodal analysis of this circuit. And of course, luckily we get the same result that we had before with superposition, and we also get the same result that we have not really written down, but that we got here from our branch current analysis. Yeah, and at the end, of course, all these methods are based on Kirchhoff's current law, Kirchhoff's voltage law, or Kirchhoff's current laws and voltage laws, and Ohm's law. So of course we get the same result, but it's always just a different way, a different procedure to write it down. So sometimes we write all these equations, sometimes we start with the Kirchhoff's current laws, and so on and so on. Yeah, and for the superposition, which was this one, we, for example, use this current divider rule, but current divider rule is also based on Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law. So it's yeah, it's not a matter of coincidence that we get the same result. Of course, we should get the same result. It's just a different way. We reach the same goal, or we reach the same destination, but just on a different path.